Today we will continue with memory interface, which we started last time. In the part 2 we are going to learn about how to interface 8088 with the memories. The only difference with 8088 and 8086 as regards to memory interface would be that here that it is going to be an 8-bit data bus. It's not going to have and 16-bit data bus. So it is simpler, and in the third part we are going to see 8086 because it's going to be little more complex than 8088, right? 8088 we are starting first because it's quite simple. It's just a simple 8-bit data bus. So the first example which we will take out here is interfacing 8 kilobytes of memory to 8088 using 2K memory chips. So obviously we will require 4 chips because total we need to interface 8 kilobytes of memory. So we need to have 4 of 2K chips. So each of this chip is 8-bit. So we have to first assign what is the address which we need to give to the 4 RAMs. So if you see for 2K memory, so these are the addresses. So if we start from 000 everything, it will end at 007FF, right? So the next one will start from 0800 and then it will end at 00FFF, and then again if you the third RAM can start at 0100 and 017FF. So you have consecutive memory 2K memory locations allocated to all the 4 memory RAMs. So this is the first step we need to do while designing a memory interface. So we have assigned the memory addresses to all the 4 RAMs and each one of 2K. Having done that, then this will be the block diagram. If you are asked to make a block diagram, you need to draw it like this, where you need to show read write signals coming to the memory chip. Data bus, you need to specify how many address lines you are going to give to the memory chip. Since it's specified that it is 2K memory chip, so you need to give a total of 11 address lines. So A0 to A10. So they are the 11 address lines which will be required to select one of the rows from the 2K different rows available in the memory chip. So this is the address lines which is coming to the memory chip. Remaining lines of the address lines have to go to an from the CPU. It has to go to an address decoding logic which will select the chip. There will be 4 such 2K chips. So one of the chip requires to be selected depending on the remaining address lines of the chip. Now we know this as I explained it in the last class. LS138. This is a decoder in which we have to give G1 as 1 and G2 and G2A and 2B as 0, and then in this configuration it is going to work like an decoder, like for all zeros the first line will be this instance active low, the first line will go low, and for 001 the second line will go low, that is O1 output 1, and for the third for the value of 2 out here, the third one will go on, and similarly for 7 the last one would go low. So this is the truth table of an LS138. And then we design RAM 1, RAM 2. In this case, so these are the data and address lines corresponding to each of these RAMs. And now you have to give the unique value out here, right, for each of them, each of the RAMs. So we start with an 00 for the first RAM, and you can give 01 for the second RAM. So these 10 lines are like from since these are the 10 different unique values which are required for each RAM. So those 10, so hence the first 10 bits of are going to be from 0000 to 7777, right? And then triple sevens, right? 7FF, sorry, from 000 to 7FF. So the first bit is, this is going to decide the selection of the chip. So this we start with 00, and this is going to become 01. The next one is going to be 10, and this is going to be 11. So it is simple in sequence in this case. So all that we need to do is we can give 11, 12, 13, like first 10 are going to be given to the chip, and 11, 12, 13 are can be used into the decoder, and 0, 1, 2, 3 can be taken as, because if you see, this is just a plain 11 and 12 are going to increase in a simple binary order, 0, 0, 0, 1, 1, 0 and 1, 1. Whereas this chip requires 3 inputs, so 13, which is assumed to be 0. This has to be 0, and these are also zeros. These are also zeros. So we can give rest of the input signals into the into a NOR gate and put it into G, and this we can give directly to. So accordingly, these one of the 4 RAMs will be selected as per the address we are at. So this is known as absolute addressing. Okay. So the advantage of absolute addressing is whenever we want to expand the RAM and all, so it is easy, because these once you have hardwired into the PCB, and if you leave a slot open, you can always put one more chip in that slot, and if you want to expand your RAM capacity, it is possible. Because if you see for the next address also, okay, if you have to, you just have to, so if a 5th RAM is added, or you can through software, and you can just access that RAM, right? Because you have used all the address lines which can be used at a later time, right? So this is, but the only disadvantage is while doing this is you will require a greater hardware. A simpler method is known as incremental address, where you permanently ground these signals, because you are now you are considering only 4 RAMs. So you permanently ground A, and you give a plus voltage in G1, and you ground these 2 signals also. Okay, so the disadvantage in this configuration is that you cannot later on, if you want to add one more RAM, it is not possible once you have made an PCB based on this design, right? So you cannot expand your RAM later on. So this is the disadvantage, but it makes the hardware slightly simple. So in some cases, in some applications where there is no requirement of expansion of RAM later on, so you can have these kind of configurations, which is known as incremental addressing. Whereas in case you want to leave slots open, and so that the user can later on increase his RAM facility, then RAM capability, then you can leave it like this and leave the address bars in those chips. So those chips will automatically get selected when you put an additional RAM in the slot. Okay, so these are the 2 kinds of.
I could explain again, sir.
Yeah. Okay. So in this case, we are placed in we are designed this for 4 RAMs, and you can keep one more slot open, right? And then you can give the same inputs to that RAM also, right? If you keep one more slot, okay, the same A12, A11, A13, and then you keep these and these also there into one more slot, and you don't push a RAM there. And subsequently, if you push a RAM into that, okay, then if you address, you can use, this is now right now spare, right? So if you give, we have used only this is as 0000 here. So software wise, if we start writing 1 there, right, and then you can obviously this output signal will be available at 4, right? So that 4 can be given to the RAM 5, isn't it? If you give 100 here.
Sir, so basically here we are dividing our 1 RAM into multiple logical components, and then are we multiplexing to see which part of which RAM should be accessed based on the address given.
Yeah. Here, we have RAMs which are available of 2K capacity. So we are using 4 RAMs to get an 8K RAMs. So we are using these. If you see, these are the starting address of the RAM, and this is the ending address of the RAMs, right? So we are using A11 and A12 to select one of the RAMs, right? So A11 and A12, A13 is permanently 0 in this case from this table. If you see for all the, so because we have to just select 4 RAMs. Okay, each RAM has got total 11 lines, and then we have 4 RAMs. So we are using 11 and 12 2 bits to select one of the 4 RAMs. So here 1, 2, 3, and 4. Okay, we got right 4 RAMs. So each of these RAMs will require 2K. So from A0 to A10 to select one of the RAMs, and then to have these 4 RAMs to select one of the 4 RAMs, you have A11 and A12, right? So since this decoder requires it's a 3 to 8 decoder, so you are putting one more bit out here, which is assumed to be 0. These are all going to be 0, and then you can select using 11 and 12. You can select one of the RAMs, right? These 2 bits will give 4 different combinations. So one of the RAMs will be selected out here. Is it okay? Now, in case you want to expand the RAM, so you want to leave one more slab for future expansion. Okay, you can do the same from this LS138. Okay, A3 can be used to chip select the 4th RAM. Okay, O4, output 4, and all that you need to have is you just give A3 is equal to 1 and 0 0. So in that case, the 4th RAM will get automatically selected. If you want few more RAMs to be connected here, so these unused lines can be used. Okay, they can in fact be terminated into the RAM slot and in the chip select line, and whenever you push a RAM into that slot, and you can just change the addressing. You can use the bit number address line 13 also. Now you use all the 3 lines instead of A13 to be 0. You can use all the 3 address lines, and accordingly use any of those RAMs also. You can cut in all those RAMs also into the circuit. Is that okay?
Yes, sir.
Okay. Whereas if you are going to do an hardware like this, if you are going to implement it like this, okay, then you can't, you don't have scope for future expansion. But then the thing is that it is now the circuit gets simplified. All these NOR gates and these things are not required now in this case. So that is the advantage. Okay. So the next example out here is interface memory to 8088 using chips available. Okay, you need ROM. All these ROMs are 2K ROMs. Okay, 2716 and 6116. Okay, this 16 stands for 16 kilobits. Okay, kilobits of memory, right? So 16 kilobits divided by 8. Okay, so you will get 2K bytes. Okay, so this 16 stands for 16 kilobits. Okay, both of them. So both are 2K RAMs. So this is 2K ROM, and this is 2K SRAM. Okay, so we need total 4K ROM, and we require 8K RAM. So we need to use 2 such chips and 4 such chips to get this address, right? So so we require, here it's written it's 2K. So we require number of required is 2. 2 of them will be required, since the total requirement is of 4K. And here again the memory chip size is 2K, and the total requirement is 4K. So we require 4 such chips. Okay, so we need to make a memory map first. Okay, so we start with 000. So this is 2K, and then from it's starting from here. Okay, it's ending here. So this is the second and 2K. So 4K has been assigned, and then we start from 8000 here, out here, right? So this you are assigning yourself, right? This value 8, and you can start with 1 also. So this is accordingly your hardware will be different. Okay, so this 08 you are starting from 08 out here, it doesn't matter. So the software needs to be implemented accordingly, and you have to note down, okay, it's starting from this value out here. So this is for starting from 8 here, we are ending this from 000 to 00 and 0800 here, and a 00 FFF here. So these are the values which you have assigned. Each are of 2K. So whereas this RAM is in sequence, all of them. So once you have done, then you make a table. These lines are going to be common for the variation is going to come in these two columns out here. Okay, for the RAM and this value, so you will have to have a unique value for, you have to ensure that there is a unique address for each of the RAMs and ROMs. If you see, these are all 000 and this is 01. Whereas for the RAM, it's starting from 1 here. So you have ensured that they are different from the ROM. So this has to be unique. Okay, accordingly you can. So this is 1. So this is 01, 10, 11. So these four, it's starting from 1, but they are 00, 01, 10, and 11. Whereas for ROM, it is 00, and then you have 00 and 01. They are the two different ROMs and addresses. So you need to make an hardware accordingly. So once you have done that, so you can write you can again use the same configuration which we did in the last time. These are going to be these are not used out here. A13, A14, 11, 12, and 15, right? And 15, because we have taken this as a different bit here to distinguish between RAM and ROM. So we take that's the reason we have taken 15 out here, right? And then 00 and 01. Okay, these are the for the ROM. If you see, this is 0 and 01. So these are the two ROMs, and then it starts from here, right? Okay. So since these two we are not using, so this is going to be this is 0, 1, and then we are starting from 4. Right, so that is the reason these two are not used, and again we are starting from 4, 5, 6, 7. So these two are not used, these two are used, and here you have given 15 out here, right? Because this is the 15th bit we have taken. We have not used these two bits in this case, right? And then we have taken an output from 4, 5, 6, 7, right? Because it is an 0, 1. If you see, it is 0, 0, 0. Then 0, 1, then it is 1, 0, 0, right? So 1, 1, 0 and 1, 1 is not used out here. 0, 1, 0 and 0, 1, 1 is not used, and that is the reason we have not used these two bits. Okay, so and then we have the next to 4 being used for selecting one of the RAMs. Okay. So not necessarily you have to have the same thing. You can design by using a bit out here also, right? You can have consecutive numbers also. Then it becomes straight and simple forward. It is just shown here just to tell you that it is not necessarily you use a sequential one. Otherwise, if you want to keep it simple, you can use 0, 0, 0, 0, 0, 1. And 0 and 1, 0, right? All the 8, there are total 6 RAMs to be used. So you can use 3 bits, and you can use a plain and simple sequence also, right? If you use a plain and simple sequence, it will become 11, 12, and 13 out here. And ROM 1, RAM 2, then RAM 1, RAM 2, RAM 3, RAM 4, and RAM 5. It will become in plain simple sequence. If you are going to use here 0, 0, just the first 3, and you put 0 zeros out in the MSBs, and you just use a plain and simple sequence out here, right? So that will suffice. And this is the kind of diagram which you will be expected to draw in your, at least in your comprehensive. So you'll have to show after the configuration what is the interconnections. So you'll have to show the data lines which are connected. So because there is 0 to 7, because it's an 8-bit, 8088, like said, it is only data lines are only 8. So the data lines are connected out here. You need to show what are the address lines which are going to get connected, what are the size of the address lines. You need to show that clearly here, 80 to 810, which is coming here, and then what are the address lines which are coming to this chip, and from where the outputs are fed to select one of these chips, right? So these connections also needs to be shown, and then you have each of these you have a memory output enable connections, and where is those output enable connections coming from. So memory read or memory, then you have output enable is connected from the output of this chip, and then you have memory read bar and memory write bar signals also coming to the memory chips. So that completes the all the interconnections required for this RAM structure. Okay, in the tutorial also I have placed one or two problems so that you have a practice of this, so you can expect such one such questions in your comprehensive exam. Okay, so today we'll stop it here. In the next class we will take on, because these syllabus are not included in your midterm in your next quiz, so I don't want to push too much of syllabus before that quiz 2. After the quiz 2 we'll again accelerate a little bit. So that's all for today. In case you have any doubts, you can ask me. No? Okay, thanks a lot.